So here I want to just sort of state without much proof some facts about Fourier that I think are important to understanding and using these Fourier series in a practical way. So here is, from the textbook, straight from the textbook, a plot of the first three harmonics of what's called the square wave. The square wave is it's drawn in green here. Actually, there's probably a picture of it up above. Yeah, here's the square wave. Okay. And as you can see here, this is a function which alternates, in this case, between 0 and it looks like pi, right? For some amount of time, it's pi. For some amount of time, it's 0. And then it alternates, goes up and down in this way. Okay? It's called a square wave. And you can compute its Fourier series, just like you would, like we've done in the past. And here are the first three harmonics of the Fourier series. You just cut off the Fourier series at n equal to 3. You sum up the first three things. You can see it here. It's reasonable. Here are the first 20 harmonics. And you can see the way that as we add more and more terms, we get a better and better approximation of this weird square wave signal. Okay? One thing that I want you to observe is how there's more error around the discontinuities in this function. There's more error that accumulates there. Okay? That's an important phenomenon that people have tracked. It's called the Gibbs phenomenon. And you can see it in more detail here. This is the Gibbs, you can see this is the Gibbs phenomenon in action from the textbook, and here is the picture here. The error between the green signal and the approximation using the Fourier series, some finite number of harmonics of the Fourier series, is large around the discontinuities in the square wave. Okay, it's much smaller in regions where the function is nice and continuous. That's the idea. In fact, you could ask, does the Fourier series even converge at these gaps in the places where the function does a big jump? And it is possible to say what it converges to. It turns out that it converges to the midpoint of the left and the right limits in the square wave. So in this square wave here, if you take a look at it, the left, like let's think about what's happening at 0, which is right in the smack dab in the middle of this picture. At t equal to 0, the left-hand limit as t approaches 0 from the left is 0. But the right-hand limit as t approaches 0 from the right, don't pay attention to my hands. As t approaches 0 from the right, the one-sided limit is pi. And so the fact is, and this is always going to be true when you're dealing with the Fourier series of these piecewise continuous functions, is that at jump discontinuities, the Fourier series will converge, and it will converge to the average value of the left and the right limits. Okay? The average value of the left and right limits. So in this case, the Fourier series at 0 would converge to pi over 2. All right? Interesting. And you can see that sort of being reflected in this argument here. Yeah, you can see that they've defined f of t to be pi over 2. They redefine the function so that the Fourier series agrees with the function exactly. Okay? But we're not going to worry too much about that because, again, it's just not that, what's happening at isolated points is not that important. Another fact that I want to say out loud while I have you here is that the rate at which this the Fourier series converges to the actual signal depends quite a lot on how nice the signal is. So for piecewise continuous functions that have these kinds of big gaps where you don't even have differentiability or continuity rather at particular points, the convergence of the Fourier series to the actual signal can be quite slow. But if you have a nice function, a nice periodic function, the convergence can be incredibly fast. As a very degenerate example of this, think about think about sine of x or sine of t. Sine of t is a 2 pi periodic function. You want to know what its Fourier series is? It's sine of t, right? All the other coefficients will be 0, and not you get perfect convergence. It's not even an infinite series, but you get perfect convergence right away with just that one term. Okay, and indeed, sine of t is a very, very nice and smooth function, beautiful function. Okay, in general, the smoother your function is, the faster the convergence of that infinite series will be to the true signal. This stuff matters, okay? This stuff matters quite a bit. What else do I want to say? Oh, right. The last thing that I want to say is that it is possible to differentiate and integrate term by term the Fourier series to get Fourier series of the differentiated or integrated function, okay? So I'm just going to leave that out there as a calculational technique and not say too much about that. But I do want to say it out loud because it is an important fact about Fourier. All right. Okay. In the next one, I want to do one last video in which I derive the solution to the Basel problem using the Fourier series for the absolute value of t. We'll see how that goes. But yeah, see you in the next one.